Hi everyone, I am Zhuye Jia. I am glad to introduce our topic, target privacy preserving for social networks. As you know, social networks are ubiquitous around us, such as Facebook, Twitter, and WeChat in China. There are lots of social networks, but many of them are rich of confidential information, such as private friendship between two users. These important but sensitive links are referred to as target links or targets, which are often the attack targets of adversaries and embed it of privacy preserving or protection. In this work, our goal is to protect the privacy of these targets. There are two steps for the target privacy preserving this work. The first step is target deletion. In our opinion, the targets should be removed first to treat the attackers that there is no relationship between the two targeted users. But target deletion is not enough because a missing link can be extensively predicted by the link prediction method. Showing an example. In this example, we assume we want to protect the privacy between the node 1 and 4. If we use the target deletion, the target link between 1 and 4 is deleted first, but this is insufficient because attacker may infer its existence, such as use link prediction. In this work, we may use the common neighbor-based link prediction. There are 3 common neighbors for the node pair 1 and 4. The common neighbors are 2, 3, and 5. There is a high probability that there is a missing link between the node pair 1 and 4. So the attacker can extensively infer the missing link out. So we need the step 2, protector deletion. In this process, a budget limited number of non-target links referred to as protectors should be deleted to help the target's hardware. So in this example, after the target deletion, we need the protector deletion. In this work, we may choose the link between node 1 and 2 and the link between 4 and 5. We delete these two protectors. The result is in the subgraph D. In this graph, the attackers may not sure there is a missing link because the number of common neighbors is very low now. So the problem can be defined by given a network G where V is the node set and E is the edge set. The target set is T and the deletion budget is K. Our goal is to optimally find and delete a set of protectors denoted by P, such that the privacy leakage of all targets can be minimized. To our best knowledge, our work is the first to consider the target privacy preserving. So there are many open challenges, such as the privacy model, mathematical problem formulation, and theoretical proofs, and optimal solutions. Firstly, we consider the privacy model. In this work, we define the privacy of outgoing hide target links. T is defined by the similarity between the node U and V, because the high similarity means high risk of the privacy for a target link. Is that right? Yes. In this work, we define it as the number of a kind of target subgraph patterns, such as the triangles. The common neighbor based is the triangle patterns, right? Also, we considered other patterns. So the privacy score of all targets is defined by the sum of every target. Then we defined a dissimilarity function, which is with the defensibility of all targets, defined by fpt. Then our goal is to find a set P that can maximize the objective function f. In our solutions, we consider the two budget assignments for the protector selection. The first is single global budget-based problem. In this model, the budget is globally used for all targets. We theoretically prove the monotonicity and submodularity of the objective function, the OP hardness of the problem, and propose a SGB greedy algorithm in which each protector is selected as the one that can maximize the dissimilarity function to achieve a near optimal solution. The second is multi-local budget-based problem. In this problem, the budget is assigned to every target, mainly used for the target, including cross-target and within-target selections. Similarly, we theoretically prove the monotonicity and submodularity of the objective function, the hardness of the problem, and propose the CT greedy and WT greedy algorithms to achieve near optimal approximation of the cross-target and within-target setting, respectively. Moreover, we do scalable implementations because in the previous three greedy algorithms, every not-target leak in the social network may be considered as a protector. This is a time-consuming process. So we further limited the alternative leaks to the ones that visit the target subgraphs to accelerate the computing speed of the three algorithms, denoted by the SGB greedy R, CT greedy R, and WT greedy R for the previous three greedy algorithms, respectively. Then we introduce the experiments in our work. We use two datasets, the arenas email and DBLP. We designed two baselines, the random selection, in which randomly removes a given number of k-leaks from the edge set. The second is the random deletions from the target subgraphs, which randomly select k-leaks from many of the target subgraphs. These two baselines are very simple. Also, we designed two local budget divisions. The first is the target subgraph-based budget division, in which the sub-budget KT for the target T is proportional to the number of target subgraphs for the target T. The second is degree product-based budget division, in which the budget KT is for any target can be defined proportional to the degree product of two edges. In the results, we first evaluate the evolution of total similarity scores of the DBLP graph, because low similarity of all targets means better privacy preserving. So this is the very direct metric to evaluate the target, the effect of target privacy preserving. In this work, we use three subgraph patterns: triangle, rectangle, and another very complex one. So we can see that in all in our experiments, the result shows that the SGP greedy achieves the best results in all subgraph patterns. Then we evaluate the running time of all the algorithms, all the arenas email graph. We mainly compare the scalable implementations and the ones without scalable implementations. As use this user result, we can see that our scalable implementations can extensively reduce the running time for all subgraph patterns. Also, we evaluate the utility because the utility of graph is very important to a social graph, which is released to the open for the research purpose. So we considered many characteristics of the social graph, such as the distance, clustering coefficient, authoritativity coefficient, cone number, modularity, and so on. In this work, we use this experiment. We do the unity loss analysis of the Reynolds meal. We set the bar. There are 20 targets to be preserved. After all targets are fully well protected, the results show that the utility loss is very tiny. Such as this example. This is the HGB greedy, the CT greedy and the WT greedy. The loss ratio is very small, about less than 5% in all scenarios or in our experiments. So that's all. And any questions? Thank you very much.